Welcome to the Dairy Podcast Show. My name is Joe McFadden, and this is my first episode, if you can believe that. Joining me today is Dr. Peter Hansen, the L.E. Red Larson Professor of Animal Sciences at University of Florida, Dr. Lance Baumgard, the Norman L. Jacobson Endowed Professor in Dairy Nutrition in the Department of Animal Science at Iowa State University, Dr. Agustin Rius, Associate Professor of Dairy Cattle Nutrition in the Department of Animal Science at the University of Tennessee. Welcome, gentlemen, to the podcast.
Thanks for having us, Joe.
Thank you.
Yeah, no problem. All right, I'm going to start with a real simple question. I want to know, what did you do this summer? And don't say that you worked all the time, okay? Because I know that always happens. I want to know what you did that was fun, that was different, that will be a long-term memory for you. What did you do?
I went to Italy and then got heat stressed.
You went to Italy. What did you do?
I had a great time getting heat stressed.
For work? Did you went there for work,
Yeah.
though? Yeah, you took time?
For work and for, we had a vacation as well. And my daughter got engaged there, so.
Oh, that's nice. That's nice.
Wow.
Beautiful weather, I'm sure, for a wedding.
But just engaged.
Just engaged. Oh, just engaged. Augustine, what did you do?
I think I'm going to follow the lines, Pete's lines as well. I visited in-laws in Spain. So we traveled there. We had a good time there. And the weather was not that bad because they live in the north part of Spain, which isn't that hot. So it was hot, but way milder than it would be here in Knoxville.
Okay. Both more travel, time with family. Lance?
Well, in between running children to soccer and hockey and violin and gymnastics, my wife is from the western part of Ireland, so we spent a couple beautiful weeks in County Galway. And so we go there, try to get there as often as possible. So it's a great place to visit.
Wow. Three gentlemen who like to travel the world here. I like it. From my end, I sold my house and I bought a new house. I actually bought a farm, if you believe it or not. I don't know what I'm getting myself into. But I finally convinced my wife to make the leap. And so we did it. We actually moved in last week. So that was a big adventure.
How many dairy cows do you have?
Not dairy cows. It's a 65-acre place right on the border of Ithaca and Dryden. It's got, I think my first endeavor is going to be maple, if you believe it or not.
Maple syrup.
Got 1,200 trees, fully operational sugar house. So looking forward to giving that a shot.
I'm looking forward for a free
samples
from a free bottle. Yeah.
Yeah, for sure. All right. Well, I invited you all here to this roundtable because you have two things in common. And the first thing is you're all pleasant people to talk to. And I thought you'd be entertaining for the audience. And the second topic is that you all study heat stress. And you primarily study heat stress in dairy cattle. And so I'm going to start with a very, simple question here. Put us all in the right frame of mind, and realizing that not everybody that listens to these podcasts is an expert like yourself. But what is heat stress? How do you define it? Is there a simple way to define it?
I define it as I teach a course in environmental physiology, so I have to define a lot of these things. I define heat stress as the sum of forces external to an animal that act to displace its body temperature from the ground state, the regulated state. So it's something external to the animal that has the potential to disrupt its physiology, depending on the magnitude of the effect and the ability of the animal to regulate its body temperature.
That's a classic, great definition. Of course, if you're a dairy farmer, though, it might just simply be at what strain causes a reduction in profitability, right? So I think there could be mild heat stress going on that doesn't cost someone money. So I guess it depends if you're a university professor or if you own dairy cows.
Well, you mentioned
maple trees.
Yeah, maple trees. Yeah. So you mentioned mild. I mean, is there ways to, I guess, define or break down the severity of heat stress?
Oh, yeah, absolutely. There are. You can take a look at the different charts that are out there. They all have limitations as per how these charts were developed and the formulas used to develop these charts. And you can have mild heat stress or severe heat stress or extreme heat stress, depending upon the temperature and humidity of the environment in which these animals live.
So, I mean, is this something that can change with time? And I'm saying as cow genetics changes over time, is how we define heat stress today, is that going to be the same definition 10 years from now? Or was it a different definition 10 years ago? Is this a sort of a fluid sort of concept that's going to change with time because of changes in environment, but changes in genetics perhaps?
I mean, I don't know. I think heat stress is something external to the cow. So it's what it is. It is, how hot it is, how high the humidity is, how much solar radiation there is, what the wind speed is. Those are constants. How does a cow respond to those changes? I mean, that clearly changes over time as we produce cows that can produce more milk. That makes them less able to regulate their physiology to deal with heat stress. On the other hand, we can modify the cow physiologically, and I know you guys have been doing that, or nutritionally, so that they're better able to cope with heat stress, or we can modify them genetically so that what would be a lethal heat stress for one cow might be a mild heat stress for another cow. The stress is the same, but how the animal responds to it depends upon the cow's genetics, depends on her physiology, her nutrition. So I feel good actually about our prospects for being able to deal with heat stress as a dairy industry, that we're learning a lot more about how the cow deals with heat stress and coming up with strategies to help the cow overcome the negative effects of heat stress.
In addition to everything Pete just said, you also have the different stages of acclimation, right? So a heat load that kills cows in early June or late May, that same heat load would not probably kill cows at the end of August, right? So you have this increase in basal heat production that Pete was mentioning, but you also have different stages of acclimation, which I think is critically important when evaluating the negative consequences of heat stress. How adapted are they?
It's something we haven't studied actually as much as we should, but I mean, you're right.
I agree.
All these studies, it's sort of, you give them a heat stress event in the last 3 days, 2 weeks, and it's constant. We're not really looking at the highs and lows, and as maybe a typical weather pattern might, it's not going to be that constant, and you can get, especially as you get these shifts and really hot events, and all of a sudden, it gets cool again. What happens to that cow in between those episodes? And is she better off in the long run? In terms of the biology behind sort of why heat stress cows make less milk, let's dive into that a little bit. Certainly a lot of effort that's been focused on this over the last several decades, but if we can try to summarize sort of the key endocrine changes, the key changes in metabolism, that the cow experiences to reduce milk production, what would they be?
Well, I think the first big issue with reduction in productivity is a reduction in feed intake. Right? They're likely reducing their feed intake to survive the thermal load, but that's probably only about half. So a portion of the reduction is due to reduction in feed intake, and then there's a plethora of other physiological changes that occur. Some of it's pathological to help describe or explain the other portion of reduced productivity, and there's a lot that goes into that other portion.
And what can you do to get cows to eat more?
Keep them cool.
Yeah, there's quite a bit of information out there in terms of feeding management of these animals, and I think you all agree with what I'm going to say. Is pretty much dated information and old information, and just because it's old does not necessarily mean that it's bad, but it doesn't have a significant amount of data to back it up. And a lot of it is association and just assumptions of different responses in metabolism due to different nutrients. For instance, fat, administration of fat and carbohydrates or fermentable carbohydrates, stuff like that, as a mean to alleviate some of this decrease in feed intake. So certainly, I think it is hard to do conclusive analysis on feed intake and nutrient intake in heat-stress animals, in heat-stress lactating cows. Just the nature of these studies are significant burdens, but I think that's an area that certainly will provide more information, more needed information to make decisions on farm. And in terms of those endocrines that you were describing, Joe, I think Lance and others have done work in the area of carbohydrates and lipid metabolism alteration in heat stress. So certainly I think there is need to do more research in that area. And that's not only unique for lactating cows. Other species have shown the shift in metabolism, energy metabolism, and there is the need to link feeding management to changes in metabolism to properly feed these animals to mitigate some of these losses in production and probably reproduction too. I don't know if.
So let me ask you guys two questions that I've always wondered about. So if a cow's appetite goes down when she's hot, just like our appetite goes down when we're hot, can we change the energy density of the diet, like through lipid feeding or increased concentrate feeding, so that when she takes a bite of TMR, she's getting more energy than she would otherwise? That's one question. And secondly, if we could stimulate her to eat more, say pharmacologically, would that be good, or would that just make it so difficult for her to regulate her body temperature that she'd be at risk of severe hyperthermia?
I'll start with the second part of it. I agree with that. I think it's not a good idea to try to push more feed in an animal that is already thermologically challenged because of this metabolism of the animal. So it's just fueling more gas, if you will, to the fire that is already there. So I think there are other means from my perspective, I think the intervention ought to target improvement in the nutrient utilization, more so the metabolism of the animal, the way these animals harvest energy out of fuels, as opposed to feeding more in an animal that is deficient in the way they handles nutrients. That would be my perspective.
Yeah, I think that's kind of spot on. To your first question, Pete, yeah, these are not just in the dairy industry, of course, but in almost all animal industries, there are summer rations, and they typically have higher fat content in them, maybe a little bit higher protein. Based upon the assumptions that we want to maximize the nutrient intake per every bite. And your second question, I think, is also spot on. If you force feed a severely heat-stressed critter, they will die. Now, if you force feed an infected animal, now I was hoping to go down this route a little bit, because I think an immune-activated animal and a heat-stressed animal, there's so many similar biological footprint of the two, I don't think it's a coincidence. But if you force feed a heat-stressed critter, they die. And if you force feed an infected animal, they also die. So they're going off feed for a damn good reason.
Right. That's what I would have thought.
What can we learn about, I guess, there's a lot of discussion about how the dairy cows sort of suffers from a heat stress event more so than other domestic animals. What can we learn about those other animals in terms of how they cope versus the cow?
How do you compare apples to apples, I would say? That's my first response to that question. Other animals, they are able to cope. Say, for instance, calves, I'm thinking about same species but smaller in size, are able to cope with heat load way better than a lactating cow, just because of the size of the animal and the surface area of the animal. So I would say it's it's hard to compare among different species. When you start teasing out the differences among these species, then it's not as simple, at least from my perspective, not as simple as it is based on what I understand.
Yeah, but I think Pete is kind of, let's just take three critters that we're all familiar with. The cow, obviously. Then you have a horse. Now, a horse can tolerate a massive amount of heat, and because they're such great sweaters, right? They'll literally lather up with sweat. And then you take a pig who doesn't sweat really at all. They have dysfunctional sweat glands. So the three, and then the cow is somewhere in the middle. So what Pete's working on with the slick gene, I think, has just an enormous amount of opportunity. If we could get the cow to sweat like a horse, or at least to sweat better, right? And they'll be able to dissipate more heat via evaporation. I just think there's an enormous amount of opportunity there.
Yeah, so Pete, I had a question on here. Breeding slick Holstein cattle for improved heat tolerance. So talk about that if you could. What's the biology behind that?
Yeah, I know. Yeah, I'll be very happy to do that. But, it's very interesting, right? Like the dairy cow is like the great example of how humans can modify animals to improve the efficiency of production of food for human beings. And, the modern dairy cow has such a smaller carbon footprint in terms of production of food for humans than the dairy cow in 1940 or the dairy cow in much of the world that's not been improved. So, we should congratulate ourselves on that. And I think the modern dairy cow is a very humanely raised animal. But the consequence of producing so much milk is she produces tons of heat and metabolic heat. So that makes her very susceptible to heat stress. One thing, if you select cows for resistance to heat stress genetically, you select for lower milk yield. So there are genes that are related to thermal tolerance independent of milk yield. But, indirectly, we have selected cows to be more susceptible to heat stress. So the slick gene is a naturally occurring mutation, very interesting, really, in the prolactin receptor gene. So prolactin receptor is very important protein for, I think prolactin probably has at least 300 biological functions. So just about every organ is regulated by prolactin. So a mutation in the prolactin receptor, that's a pretty big deal. But if you look at breeds of cattle in the Caribbean and South America, there's at least 6 mutations that have arisen in the prolactin receptor. So 6 different times in evolution, the prolactin receptor has been mutated, and it causes a very short hair coat. And one of the roles of prolactin is to inhibit hair growth. So these so-called slick animals have a mutation in the prolactin receptor, causes them to have very short hair. And because they have short hair, they sweat more. They probably lose more heat via conduction and convection from the hair coat because it's shorter. And it's been shown over and over again, they regulate their body temperature better than a half sib that didn't inherit the slick mutation.
Is that mutation only on the sweat gland itself, or is that throughout all the cells?
It's everywhere. So, that's one question. What is the implications of that mutation for liver function, for immune function, for mammary gland function?
Do they make as much milk?
Yeah, I don't know. I think they do, but we really need more data on that. The work we've done, which is with few numbers of cows, they produce as much milk in the winter as animals without the slick mutation, and in the summer they produce a little bit more milk. And in Puerto Rico, slick Holsteins produce a little bit more milk than animals without the mutation. And we've looked at gene expression in the liver It's mostly the same in slick and non-slick Holsteins, but a little different. A few genes were differentially expressed. So we do need to understand the mutation, but it cannot be a deleterious mutation or it wouldn't have gotten selected for 6 different times in cattle evolution. So the gene got put into Holsteins accidentally. I think in the island of Puerto Rico, the gene is quite frequent in Holstein populations, probably because the Holsteins that came to the island were bred with local cattle, which had the mutation. And then here in Florida, a dairy farmer got some free Senepol semen, which Senepols have the slick mutation. So just to see what they look like, he bred his Holsteins to Senepol bulls. And lo and behold, half of them had really short hair coat. And Tim Olson at the University of Florida identified that phenotype and bred the animals back to Holstein since the 1980s and retained that slick mutation. And, now that same cross has been done in New Zealand to produce slick-haired Holsteins, slick-haired Jerseys, slick-haired Holstein Jersey crosses, and gene-edited slick animals have been produced: Holstein, Jersey, Angus. So the gene is getting a lot of interest, and it does definitely allow animals to regulate their body temperature better during heat stress. There's less data, but it probably reduces the impact of heat stress on milk yield in the summer. And maybe reproduction. At least in Puerto Rico, the slick Holsteins have a shorter calving interval than animals without the mutation. So, what I would say is it's very cool, but there's probably other mutations that we haven't discovered yet that exist in Brahmins, other adapted breeds of cattle. And we should bring those into the Holstein as well.
You mentioned reproduction there for a moment, and I was reading one of your papers, Pete, and I'm sort of going to quote you, okay? And that quote was, "The increased heat production caused by milk synthesis makes lactating females less able to regulate body temperature and more sensitive to the anti-fertility effects of heat stress than non-lactating females." I guess I just wanted to just go into that a little bit more for me, help me understand what those anti-fertility effects of heat stress are, and how can we sort of combat them? This would be my next question.
Yeah, I want to change that statement a little bit.
We can't retract the paper yet.
No. No, it's true. Animals that produce more heat, animals that produce more milk, are less able to regulate their body temperature than animals that produce less milk. And a higher body temperature causes infertility. Oocytes very susceptible to elevated body temperature. The very early embryo is susceptible to elevated body temperature. The reason I want to modify that statement a little bit probably relates to some of the work Lance has done and other people. We did a study last summer down in South Florida. So we looked at body temperature regulation in Holstein and Brown Swiss. So the Brown Swiss produced less milk than the Holstein. And during the summer, Holsteins have higher body temperature than Brown Swiss, like you'd expect. So then we looked at summer-winter differences in milk yield. And we reasoned, because the Holsteins have a higher body temperature, they will experience a greater reduction in milk yield in the summer. But we didn't find that. The percent reduction in milk yield was numerically actually higher in the Brown Swiss than in the Holstein. So even though the Holstein are less able to regulate their body temperature, at least on this one farm, And, maybe it's just specific to that herd of cows that have been selected naturally for thermal tolerance for a long time. But at least on that one farm, Holsteins produce more milk, less able to regulate their body temperature, but they don't experience any greater reduction in milk yield. So maybe some of the things that like Lance is talking about and others are talking about in terms of changes in gut permeability in response to heat stress, or some of the endocrine changes in response to heat stress. Maybe there's some differences between Holsteins and Brown Swiss that allow the Holsteins they still experience a drop in milk production, but maybe not as much as you'd expect because of their increased body temperature, because there's other things different about them. So, maybe that's true for fertility as well. No doubt, the higher the body temperature, the lower the fertility. But, there may be differences between animals and how they respond to higher body temperature.
That's very interesting, Pete. It's very, very similar to what we've measured and reported upon in pigs. And it has implications, of course, to genetic companies when they're selecting sires, right? What type of phenotype do you hang a hat on with regards to genetics? Because in our experiments with pigs, it's the pigs that get the hottest during a heat stress event aren't necessarily the ones that do the poorest from a feed intake and average daily gain perspective. Yeah, so it's just, it kind of fits perfectly with what you're saying is ultimately the producer, the farmer, wants an animal that can produce, right? And more interested in economically important phenotypes rather than body temp.
Yeah, I've changed my own thinking on that. Yeah.
I think add to that a little bit. When you look at the data from 50 or 60 years ago, I was just reading Stan Curtis' textbook, and this is known for the fact that the relationship between physiological parameters and productive parameters aren't necessarily linear, or not even a relationship at all. It's been known for years, so it's one of the dogmas that we still see out there, and we have to make sure that people understand, or at least explain our point of view, to make sure that the hottest animal doesn't necessarily mean it's going to be a more severe effect when it comes to production. And I don't know, piggyback on what Pete was saying a moment ago, I don't know about you guys, but I've noticed a lot of variability in our responses, particularly physiological responses in animals on heat stress compared to non-heat stress or thermoneutral animals. And in some animals, they get, so talking about cows, 100, 120 breath per minute, or say 104 degrees Fahrenheit. And they're just having a great time. They're just laying down, they're just eating, they're not suffering as much. And animals that under the same conditions don't even, increase a few, 1 degree, if you will, in, just 65, 70 breath per minute. So the individual response to the same heat stress treatment, it's amazing. So obviously, at least in my mind, it has to be some genetic component that goes beyond the ability to the animal to sweat and cool off quicker. I think it is something else, maybe hormonally, maybe like immune response to different stimuli and things like that goes beyond the general idea of it's part of it, right? It's part of the response, but I think we have to look more beyond the normal thermoregulatory mechanisms that allow the animal to cope with regulate body temperature.
Well, let's dive into the. I think you mentioned immunity, and it's been discussed by both of you. that leaky gut buzzword that I think Lance coined so many years ago. Maybe others, I'm sure, before him. But I guess where are we at in terms of the gut permeability part of this story? I mean, my lab certainly has tried to catch up with others in this area, and we just had a paper published looking at total tract gut permeability in lactating cows, and we showed that by day 3 after a heat stress event, they develop increased total tract permeability, and it remains for 2 weeks. But when you look at animals that were pair fed, that response wasn't so rapid. It was more delayed. I guess I want to hear from you, Lance, in terms of how much of an impact does a leaky gut scenario have on milk production?
I read your paper closely. It's a great paper, right? Because it's really the first time that's been demonstrated conclusively in dairy cows. We've all assumed it's going on in dairy cows, but your paper really solidified that. And it's been shown in pigs, rodents, humans, right? This is a highly conserved, goats, highly conserved response amongst hyperthermia. And so, our group, I may be a little biased, but we're pretty strong believers that this leaky gut plays a key role, right? The gut becomes permeable, get infiltration of probably thousands of different antigens, maybe tens of thousands of different antigens now through this permeable gut wall, and you have an immune response. That immune response is very energetically and amino acid-wise very expensive. And of course, an activated immune system now becomes the highest priority for any animal, not just the lactating dairy cow. So synthesizing muscle, milk, a baby, whatever, wool becomes de-emphasized, and mounting this immune response becomes a very high priority. So we think it's pretty central, right, to this other. Remember earlier we talked about reduction in feed intake? There's this other portion that's not related to reduced feed intake, and that's why I mentioned earlier. I think the physiological footprint of heat stress versus the physiological footprint of just simply immune activation could be mastitis, metritis, pneumonia. I don't think it really matters. These two footprints are almost identical, and I don't think it's a coincidence. Essentially, a heat stress cow is an immune activated cow.
So I know people ask me all the time about the microbiome, and I'm not a microbiome guy. I say that all the time, and I'm not going to be that guy. It's nearly impossible for me to try to wrap my head around the biological implications of the microbiome in the cow, at the lower gut especially. But I guess I want to hear from others that maybe be a little bit more confident in terms of what role does it play? Are there obviously endotoxin? Everybody talks about LPS, okay, but are there other sort of metabolites perhaps that are gut-derived, microbial-derived metabolites that could be potentially influencing gut barrier or the immune system, immune activation that we're not paying attention to it, but we should?
Dave Beatty and Jill Davidson did all these experiments where they were exercising cows, and I think people used to laugh at them. But there's an old paper from the 80s, I think from Hale's lab, where they exercised sheep. And the sheep were more resistant to heat stress because they had increased cardiac output. So the reduction in blood flow to the gut was reduced. The reduction in blood flow to the gut during heat stress was reduced because they had a greater cardiac output. So, I think, what Lance is talking about is got a lot of relevance for responses to heat stress. So there's probably ways to modify gut integrity or modify blood flow to minimize some of the effects. And of course, if the gut is leaky, LPS comes out, which causes hyperthermia.
Exactly.
We did an experiment several years ago after I read that paper on the sheep where we gave banamine during heat stress to see if we could lower the hyperthermia, which did not work. But I think there's, it's a new way to think about how heat stress is affecting cows and other animals.
I'm laughing a little bit because we did a similar project where we gave it right after calving, and it was kind of a train wreck as well. But to your question, Joe, about the microbiome, I'm also not a big microbiome guy, but there's a lot of things made by microbes that have potentially pathogenic capabilities. Ethanol, these amines that are made from amino acid fermentation. I think there's a lot of things, not a lot of noxious compounds created during an altered fermentation that potentially has negative consequences to barrier function.
Yeah, I'm also not a microbiome person by any means, but just looking at the literature, just reading some of the literature out there, you have the commensal microorganisms and the potential pathogenic microorganisms. So the disbalance of the dysbiosis, which is the equilibrium in which these microorganisms live in the GI, leads to all these different altered metabolites or secondary metabolites that are produced by microbes, and endogenous metabolites that are handled by commensal bacteria that no longer there. So example of that, I think there's hepatic outputs of different products that are handled by microorganisms in the gut that were not there. Then these metabolites are not function properly. So I think there's more than just pathogenic microorganisms. Like Lance was saying, there are thousands and thousands of antigens, and they come in different forms and in different forms. So yeah, it's quite complex. I would refer to the studies in which they look at the microbiome on pigs, on rodents that are prone to obesity and with diets, high fat diets, and how this microbiome play a role in developing obesity and diabetes. So that's those studies are available out there. Those kind of studies illustrate the point of importance of a healthy microbiome from an animal standpoint. From the heat stress standpoint, I think there is a lot to learn, and I don't know if we have the tools to get there, but it's certainly something that requires more research.
All right, let's transition towards the end here, talking about potential solutions and sort of the cutting edge of the field. There's been some interest, I know, Augustine, that you've looked at, I think, post-biotics. I think you did a calf study where you're looking at sort of dietary post-biotics. What is that? What are post-biotics, and what did you observe?
Well, that's an interesting question. So I just want to allude a little bit to these anti-inflammatory interventions that Pete and Lance was referring to. We did a study recently in which we used dexamethasone as an anti-inflammatory intervention. Of course, dexamethasone has other consequences. It's a potent anti-inflammatory drug, but it also has other consequences to metabolism. But overall, we found interesting results from the phenotype standpoint. The animals performed fairly well under heat stress conditions treated with dexamethasone, and they were comparable to the counterparts on the thermoneutral group. And these are calves. So this molecule, this product that you, Joe, are referring to, has been shown to mitigate some of the inflammation that is going on in heat stress cows. So inflammation measured by acute concentration of acute phase proteins produced in the liver. So there are different ways to assess inflammation. So if you follow these acute phase proteins produced in the liver upon inflammatory insult or inflammatory response, well, you can you can you can say that you're in the presence of inflammatory response. So the post-biotic is basically a product of yeast that has been fermented and harvested under controlled conditions, and these metabolites that come from these fungi are used to mitigate inflammation. And at least we think that that's part of the mechanism of action for this product. The objective of the study was basically to control the inflammatory response or reduce the tone of the inflammatory response to mitigate the inflammatory response observed under heat stress conditions. And that appeared to actually had a significant positive response in these animals. And we did a study in heat stress cows, and we also did a study on heat stress calves. So overall, depending upon the variable you look at, so, if it is heptoglobin or serum amyloid A, or depending on the problem of interest, overall you see a response, in other words, a reduction of these acute phase proteins, and more importantly, we see an improvement in performance. So whether the amelioration of the inflammatory response is responsible for the improvement in production remains to be seen, but there appears to be an association between the two.
All right, there's one possibility. Lance, you presented at the ADSA annual meeting about zinc. What's the mode of action for zinc?
Well, yeah, our group's been spending quite a bit of time trying to identify target molecules that can help improve gut integrity, and zinc is one of them. And there's others, antioxidants. And
how does zinc work?
Well, that's a damn good question. I'm not 100% sure how it works, but it's been evaluated in multiple models, not so much on heat, but from like an irritable bowel, Crohn's disease perspective, and human doctors have been using zinc as a method of improving gut integrity for a long time. How it works, it might just simply be upregulating heat shock proteins that then help anchor in these tight junction proteins in the lateral side. I think we also need to just admit, though, that at the end, as of right now, the best way to prevent heat stress is via modifying the microenvironment of the cow, right? Shade, evaporative cooling, and fans.
Yeah, so people mention it all the time, and there was a study in Journal of Dairy Science, I think, that tried to quantify sort of the improvement in performance that you could have with these strategies, and it's not complete, right? It's around the range of 60%, I think, is what I read. And there's also concern there that some of these approaches are not necessarily helping the dairy industry become more sustainable, and so I think there's challenges there, right, that we have to sort of face.
Right, these are investments the producer has to capital investment the producer has to invest in, and of course, in some developing regions of the world, they don't have the capital to do that. So I think we need to continue identifying and looking for dietary strategies that can help ameliorate the negative consequences of heat stress, and continue looking at the genetic component like Pete is. And but yeah, in North America and Europe, where there's more resources, still that should be a producer's first investment, right? Is modifying the environment.
Like, I'm all for. I mean, my research is focused on things other than changing the environment of the cow. So I completely agree on the importance to do that. But I will say, here in Florida, Bob Collier always used to say, when a cow dies and goes to hell, she goes to Okeechobee, Florida. It's very hot here. And cows today in Florida are much less affected by heat stress than when I got here in the 1980s, even though they're producing more milk and even though it's hotter. And that's because of investments in facilities, that cows are managed in housing that, provides a lot of relief. So yeah, is it sustainable? I guess that depends how you define that. Is it expensive? Yes. But of course, we're in a country where milk price is high. You can make that investment and get a good return. Sub-Saharan Africa, maybe it wouldn't be cost effective to invest that amount of money in facilities. So all the solutions, I think, need to be explored. But I think, we really should feel good as an industry that we've, I don't want to say met the challenge of heat stress, but we have come a long way to providing people with tools and maybe sometimes the dairymen came up with the tools and then we studied them. They work. But, I think everything needs to be looked at.
If I may add to that, I think there is work coming out of Wisconsin also showing the deficiencies in facilities across the U.S. Maybe Florida is ahead of the rest of the warmer states in the South. But certainly there is deficiencies in the facilities, in the current facilities, to properly handle and prevent heat stress. So maybe, Joe, you were afraid to. So think, for instance, a producer up north that only faces heat stress 2-3 months over the year. For that producer, maybe investing in proper cooling for 2-3 months of the year might not be a feasible option, or I don't know, I'm just thinking out loud. So whatever the rationale behind these deficiencies, the deficiencies are real, and there's people studying these deficiencies, whether it's insufficient airflow or facility design, what have you. Other states do face this facilities limitation to properly handle heat stress.
Okay. My final question is, I want to know where we got to go next. Like, what's the biggest thing that excites you the most in terms of the science, of the biggest potential for improvement? And I'm sure there's going to be a lot of different answers here, but Pete, we'll start with you. Where do we got to go next?
What excites me is the genetics, and probably for a lot of reasons. But, I live in Florida again. We have a lot of Brahman cattle down here and Brahman influenced cattle. You can't help but look at them and see how resistant they are to heat stress, to realize, and some of that's because they don't grow that much. They don't have big digestive tract, but still, it just makes you realize there's a lot of genetic variation out there and how animals cope with the environment that we can exploit.
I think Pete is on to something here. I think that genetic component is probably going to provide opportunities to make significant progress. In the meantime, because I don't work in that area, I will continue working in the other response associated with heat stress, which is metabolism and things of that nature, which I think also play a key role in the overall response of a heat stressed animal.
Well, I'm still going to keep targeting the gut and the gut barrier integrity. One, for heat stress, but I also think that this hyperpermeable gut also explains some of our poorly transitioning dairy cows, transport stress, weaning stress, and a transcend species. So if we can identify a molecule that can do a good job at improving gut integrity, I think there's opportunity for it to transcend species and be a multi-trillion-dollar product is there.
Yeah, I will say that we will soon announce we've done 2 transition cow studies here looking at total tract gut permeability, prepartum and postpartum, and there's some exciting data coming from that. I hope to share that soon. Well, I want to thank the 3 of you for joining me today. This was certainly my first time being host for the Dairy Podcast Show. You were all excellent guests, and I thank you for your time. I look forward to see what develops from your lab in the near future. And that's all I have to say. Thank you.
Thanks, Joe.
Thank you.
Thank you, Joe. Thanks a lot.
Good seeing you guys again.